All right, let's talk about the concept of transformers right here. And the way that we're going to use transformers isn't by changing 18-wheelers into alien fighting robots. That's way more exciting. But we are going to be transforming current and voltage using two inductors. So if I have inductors on one side, let's call this the primary side. And then I have an inductor over here, and we'll call it the secondary side. Whenever I send a change in current through this coil, it produces a magnetic field. Whenever that change is happening 60 times per second, if we're thinking 60 hertz, that's what's in our wall, 60 times per second, it's changing. Well, this magnetic field is hitting this other set of coil on this other side. And so whenever that happens, a current is induced out this other side. So if I have going into my windings, what we call I primary, well, as long as I have that AC current, I have I secondary. This wouldn't work with DC because in DC it's not changing, but in AC it's changing 60 times per second. So I have these coils that are creating the magnetic fields and these lines of green flux. I'll erase my flux now. And I have my windings on the primary and the secondary side, and across them I have my voltage that is dropping over here. And if you look at the way the current is going, it's rising over here, V primary and V secondary. So on the primary side, as the current's coming from a AC source, it's acting like a load, but then this new current coming out on this side is acting like the source. It's the voltage rise on the secondary side. But the main thing that we're going to stick with is primary and secondary side of these windings. Now, what is actually transforming? If I kept the coils and I had 20 windings spun around inside my inductor and I had 20 windings spun around on the other side, nothing would transform. I could send the current over, but it wouldn't change it. What's changing is this transformation ratio down here. We'll talk about the winding direction down below when we talk about dots, so we'll come back to that. But this transformation ratio is saying the number of coils that I have. So if I had, also called the number of turns, right? If I had 20 coils or 20 turns spinning on one side, and I had 10 turns or 10 coils, 10 spins on the other side, then I would have a ratio of 2 to 1. Pretty straightforward. I could also say that I have is A of a turns ratio of 2. It's another way of saying the same thing, right? This turns ratio, and that turns ratio is directly proportional to these voltages on each side. So on this one up here, I'll just draw a new one, but I have coils on one side and coils on the other. And so if I said I had a turns ratio of 3 to 2, and on this side I had 90 volts across this, well, I can basically do that on my head. 2/3 of that would be 60 on this side. So I have 60 volts across that side. So that is called the turns ratio of what's producing out. Note that all of these things are ideal. Everything that we're dealing with is an ideal transformer. There's no losses that we're losing. Really, there is some flux losses and resistance inside the coils, but we're not going to deal with that because this is 301, not 331 or the double E class. So this one that I just drew on the right with a turns ratio of 3 to 2, that would be a step down transformer because I went from 90 volts down to 60 volts, or my turns ratio was greater than 1. The turns ratio here, in case you're like, wait, what is he saying again? Well, it's just 1.5. That's my turns ratio. From 3 to 2, it's a turns ratio of 1.5. So if it's greater than 0, or sorry, greater than 1 right here, then it's a step down transformer. Let's draw a step up transformer and keep it simple, right? If I had, say, 1 to 30, and I had 2 volts across this one, well, in my turns ratio, I have 60 volts across this one. Pretty straightforward math. So this one right here would be a step up transformer. This one right here would be a step down transformer. So It's a matter of which one has the greater windings on that side. How does current work with this? Well, this is an ideal transformer, so the power into the transformer and the power out of the transformer are going to be the same. The energy is going to be conserved, all right, at that law. And so if I consider that I have these coils, these inductors on each side, and I have a current coming in right here and a current coming out right here, well, since energy is conserved, this actually switches. That A, I don't know why it's written that way in these notes, but the A right here is I secondary over I primary. It's reversed from what we were looking at on the voltage. So say that I had 10 amps flowing in here with a turns ratio of 2 to 1. Well, instead of going from down to 5, this would be 20 amps on the other side, right? See how it swaps? And so on the flip side of that, if I had a turns ratio of 1 to 3, and I had 9 amps going into my primary winding over here, well, then on this side, I would have 3 amps coming out of those windings. Note that everything I've been doing, and I've tried to write it, but it's with magnitudes, right? See the I secondary, it's not bolded on the equation sheet, and it's not a vector on top. I've been writing it as magnitudes. The way that we determine what the angles are, right? If I'm thinking of what is I secondary, well, it's made up of the magnitude of that with an angle of the theta of I secondary. And so where are we going to get this theta? Right here, it's from the dot conventions. And what this is, think about the windings up top. If I wrap them both in the same, where they're both going in, see how this one's coming across and going in? So their dots match. And what that means is if the dots match, then the angle is the same for both the I primary and the I secondary, or the V primary and the V secondary. And then if the dots are opposite, dots opposite change by 180 degrees. And you add or subtract it just to basically keep your range within 0 to 180. So we're going to keep our range within 0 to 180, so you can add or subtract the 180 to keep that. But the dots are going to be opposite, or they're going to be the same, right? You can't have the windings any other way. So these transformers have a ton of practical application, and I'll make a video, or I'll share a video for the next lesson to kind of see the inner workings of the transformer. But most of these things are going to be rated with an S, right? Here's apparent power. Right there would be S apparent power. And it's going to be telling us what the voltage on each side is. So if it says 2400, 120, then this is a step down transformer going from 2400 volts down to 120 volts. You could even consider, what is the turns ratio there? A equals 2400 divided by 120, and I get 20 as my turns ratio. So that's the turns ratio of that. Most of the time, we're going to put iron cores to get a better transmission of these, or we can use an air core transformer in some applications where we don't put the iron on the inside. But either way, what's happening here is there's so many coils inside of here that you can't even see it. It's being protected, but this iron core is helping the lines of flux to move more smoothly and to make it more ideal. And like I said, everything in this class we will be solving with ideal.